That's not the case here, but the products are the same. So the double arrow tells you that in the beaker in which this reaction is being run, you're going to get a little bit of this, a little bit of this, and a whole lot of this. Okay? So that's what insoluble salts are going to do as well. So now we can go back to our lead, lead to arsenic. Now, if you go to the charts and see if you can find that to prove yourself that this is an insoluble salt, you will find that on page 772 and page A18, you will find that compound listed, and they also give you the name for it, which is really important. This is called lead to arsenic. Now, the deal with lead and tin and bismuth is that while they are main group metals, they are found in the A columns, they tend to have two charges, so they act like they are transition metals. And it's because of the large number of D and in some cases F electrons that keep shifting around. But it's either going to be 2 or 4 for lead and tin, and either 3 or 5 for bismuth. And how do you know? Well, you have to look at the formulas here, and the fact that they give you the name tells you lead to arsenic means that the lead here has a positive 2 charge. Now, if you multiply that by the number of leads, that gives you 6. Positive 6. Arsenate here, if you take a look at your polyatomic ion chart, arsenate here is -3. And you're going to multiply this by 2, and you get -6. And positive 6 and -6 add up to 0. Lead cannot possibly be 4 in this context, so the name will help you do that. So the two things that you have to look at is look at the name, find the Roman numeral, that is the charge of the lead, and then look at the polyatomic ion chart, find the formula and charge. Well, you don't need a formula, it's given you, but you do need the charge to make sure that this is indeed correct. But you don't have to, but you do need the charge for the separation of the ionic compound. So this is found there, and this tells you then that this is an insoluble salt, which is the version of being weak as far as breaking apart. So we treat this as if it's weak, just like we did with the acids. So we're going to take Pb 3 ASO4 2, but we're not going to put aqueous down here, okay? Because it's not dissolved. This is going to stay in solid form. But we're going to use a double arrow here. Now on the script, I don't have the capability, or with my computer, of putting something above the double arrows, but technically you should have an H2 on there. So every time you see a double arrow, an insoluble salt, you have to imagine the H2O goes up there to explain the phases you're going to get over here. So you got 3 leads. Now don't put Pb3 because lead is not triatomic. There's no such thing as a triatomic metal, and it's not even metal, it's an ion. So we have to put Pb 2 positive here, but the 3 actually goes in front, saying that when it dissolves, it's going to break down into 3 lead 2 ions. And that is going to be dissolved in water. What tiny amount is going to be dissolved in water, we're going to use aqueous for that. We have 2 arsenates here. So plus 2 ASO4. The charge of that, like we said, is 3 negative, and this is going to be aqueous. Now, you're going to have a temptation to take the parentheses and move it over here. Resist that temptation. These are ions by themselves, not combined with a metal. When you combine this into a compound, you need parentheses to explain the subscript 2 here. But when you have free ions, they will not have any parentheses involved in them. This is the chemical equation explaining the partial breakdown of lead-2 arsenate into 3 lead-2 ions plus 2 arsenate ions aqueous. Okay? All right. So that's what we had there. Okay, let's make sure. Okay. Now the next compound, we did this one already, so that would be done. The next one is K2SO4. So, K2SO4. We go to the charts to see if they're there. Well, we don't really need to, do we? Because the K there tells you that is a group 1 metal. Ion. So that means it should be 100% soluble. But to double check and make sure that you are correct, if you have lingering doubts, particularly when you're doing this for the first time, check the charts, see if they're there. Or see if that's there. It's not there. So this is going to be analogous to a strong acid. It's going to be a single arrow reaction breaking down completely. So this is going to be K2SO4 aqueous. And we can't put aqueous because we know it's 100% soluble. Because we can't find it in those insoluble salt charts, and the fact that it has group 1 metal. Now, in order to do this though, we're going to have to know the charges of these 2 ions. Well, this is a group 1 metal, so that's a pretty easy get. That's going to be positive for each one. And even though there's a 2 there, that's just there to satisfy the charges here. Sulfate, one of 2 ways to find the charge for sulfate is by looking at the polyatomic ion chart, finding SO4, you see that it's -2, or realize 2 times 1 is positive 2, so this has to be -2 in order for the charges to add up to 0. Whatever process you use is fine as long as you get the right answer. But you must include the ions in your products. So you have K. Now K is not diatomic, so that little 2 that's there does not come over here as a subscript. And we'll come back to that. And that's positive, and that's going to be aqueous. And then SO4 has a charge of -2, which we'll write as 2 negative. And that's going to be aqueous. And we can put water above this, but the fact that this is aqueous is not necessary. But now we need a balanced equation. We have 2 potassiums there, 1 potassium there. Now we use a coefficient 2 there, not a subscript 2, to balance the charges. And that's how it's done. So this lesson is all about writing the appropriate dissolving reaction or dissolution reaction using single arrow if it's soluble and double arrow if it's insoluble or slightly soluble. So, any minute now, your practice problems, do the balanced association reactions for these 5 compounds. Okay? Have fun.